Hello, my dear students. Welcome to the session. Continuation of important observations from power electronics concepts. In this session, with respect to Module 5, I would like to discuss about AC voltage controllers and cycloconverters concepts. All of you concentrate. First, we have to start with the AC voltage controllers. Students, we know that AC voltage controller is a static power electronic circuit which converts AC to AC with variable voltage. That is, voltage is variable but frequency is constant. This point mainly you have to remember. That is, in AC voltage controllers, at output side voltage is controlled but frequency constant. What do you mean by frequency is constant? For example, input frequency is 50 Hz, then output frequency is also 50 Hz in AC voltage controller. That is, frequency remains constant, only voltage is controlled. This AC voltage controllers is also called AC voltage regulators or RMS voltage controllers. Then what are the different types of AC voltage controllers? One is a single phase half wave AC voltage controller using R load that you have to concentrate. This is the circuit configuration of half wave AC voltage controller. This half wave AC voltage controller is also called unidirectional AC voltage controller. Half wave AC voltage controller is also called unidirectional AC voltage controller. It is a combination of thyristor and diode. That is, it's the anti-parallel connection of thyristor and diode. A half wave AC voltage controller, half wave AC voltage controller, AC voltage controller consists of anti-parallel connection of thyristor and diodes. That you have to. Let's assume that RMS value of supply is Vs. Then positive half cycle thyristor will conduct, negative half cycle diode will conduct. Then analysis is very important. In a single phase half wave AC voltage controller or unidirectional AC voltage controller, the average output voltage is equal to Vm by 2 pi into cos alpha minus 1. What the average output current, students? I naught equal to V naught by R. What the RMS output voltage? RMS output voltage equal to Vm by 2 root pi. It's a 2 pi minus alpha, important. 2 pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by. This is the RMS output voltage. And you also concentrate input power factor formula. Input power factor equal to V naught. Direct formula also you can expect. In the half wave AC voltage controller or unidirectional AC voltage controller, the input power factor equal to 1 by root 2 pi into 2 pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of. This is also RMS voltage formula. This is the RMS voltage formula in terms of Vs. Previously that I given RMS voltage formula. Na? This is in terms of Vm. This is in terms of Vs. How to write Vm and Vs relation? Vs equal to Vm by root 2. Vm by root 2. That I am replacing Vm by root 2 by Vs. Then I got this formula. In any form, they will give the formula. We may expect formula directly from Vm form or we may expect formula directly in terms of Vs form. That is very important. And one of the main drawback of half wave AC voltage controller or unidirectional AC voltage controller is if we control the firing angle from 0 degrees to 180 degrees, the output is controlled from 100% to 70.7% only. That is very narrow range control. By using half wave AC voltage controller, at output side, the output voltage is controlled for very narrow range. Very narrow range, how much range it is controlled? 100% Vs to 70.7% Vs, friends. 100% to 7, nearly equal to 71%. That is 29% only it is controlled. 100% to 71%, na, nearly it is controlled by 29%. Because of this narrow range controller, this controller is practically not preferable. Sir, why this much of narrow range control is exist in half wave AC voltage controller? Because of the diode. In one half cycle diode is present. Na? If diode is present means negative half cycle we can't control the output voltage. Only positive half cycle only we are controlling. Because of this reason, in half wave AC voltage controller, the narrow range voltage control is exist. With respect to half wave AC voltage controller, you have to practice these questions. Whatever the formulas that I given now, based on that formulas, you have to practice this one. Here I'm not given the waveforms. Mainly analysis is very important. That's why taken the directly analysis. And what is the RMS output voltage? What is the RMS output current? What is the output power? What is the input power factor? Any problem you can expect, you're ready to answer. Next, one more configuration of AC voltage controller is single phase full wave AC voltage controller using R load switch. It's a full wave AC voltage control. This full wave AC voltage controller is also called bidirectional AC voltage control. It is also called bidirectional AC. But half wave AC voltage controller is unidirectional AC voltage controller, but it is a bidirectional AC voltage controller. That is, it consists of anti-parallel connection of two thyristors. But previous circuit is one thyristor and one diode. But this circuit is combination of two thyristors. That is anti-parallel connection of two thyristors. Because of two thyristors, both the sides output voltage is controlled. Positive half cycle output voltage is controlled. Negative half cycle also output voltage is controlled. That's the reason why in single phase full wave AC voltage controller, wide range of voltage is possible. Voltage control is possible. Then directly I am giving analysis. I am not given any waveforms. Directly concentrate on the analysis. What is the average output voltage in the case of full wave AC voltage controller? V naught equal to 0, because positive half cycle and negative half cycle output same we can get. That's the reason why average voltage equal to 0. For example, if the question is asked like this is the full wave AC voltage controller using resistive load now. Across they given on PMMC meter. What the reading of the PMMC meter if they ask? What the PMMC measures, friends? Average value. Then what the average voltage in full wave AC voltage controller? 0. That type of model is important. This is very important. What is the RMS output voltage of full wave AC voltage control? The RMS output voltage of full wave AC voltage control is Vm by root 2 pi into pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by. Then this is the RMS output voltage in terms of Vs. This is the RMS output voltage in terms of Vm square. Then what is the input power? Direct formula also we can expect. Input power factor equal to 1 by root pi into pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by. That is, if you control the firing angle from 0 degrees to 180 degrees, the RMS output voltage is controlled from 100% to 0%. 100% to 0% we are controlling in full wave AC voltage controllers, because positive half cycle thyristor is controlled, negative half cycle also thyristor is controlled because of anti-parallel combination. That's why it is a wide range of controller. This controller is more preferable practically. Full wave AC voltage controller is more preferable practically. And these practice questions, you have to practice this question. This is the question based on full wave AC voltage controller. It is asking that what the average output voltage? Average output voltage 0. What the RMS output voltage you have to calculate? What the RMS output current you have to calculate? What the output power strength? Output power equal to V naught RMS square by R. Then what the input power factor also you have to calculate. This is about the question, practice question with respect to single phase full wave AC voltage control using resistive. And very important repeated questions in GATE exam. Single phase full wave AC voltage controller using RL load strength. Full wave AC voltage controller using RL load. This is the repeat models of questions. Based on this circuit, the questions are framing in GATE exam. Even though in syllabus AC voltage controllers are not given, but the question is framing strength. In RL load, up to what range the firing angle is controlled. That is very important. That mainly you have to concentrate. In RL load, if SCRs are triggered with the power factor angle, that is, if SCRs are triggered at power factor angle, then each SCR conduction angle is 180 degrees. If the SCRs are triggered at power factor angle, each SCR conduction angle is 180 degrees. If SCRs are triggered at power factor angle, then what the each SCR conduction angle? That is 180 degrees. That you have to concentrate. Each SCR conduction is 180 degrees. If SCRs are triggered at power factor angle, input voltage waveform and output voltage waveform is same. Very important. Each SCR conduction angle is 180 degrees. Then what is the extinction angle? Extinction angle equal to pi plus pi. If SCRs are triggered at power factor angle. What the power factor angle here? Power factor angle pi equal to tan inverse XL by R squares. Power factor angle pi equal to tan inverse XL by R. Then T1 conducts pi to pi plus pi, T2 conduct pi plus pi to 2 pi. Then input voltage waveform and output waveform is same. If input and output waveform, this one, V0 waveform and Vs waveform. Input waveform, and this is the current waveform. Current waveform is lagging because of inductive loads. But I am talking about voltage waveforms. Input waveform and output voltage waveforms are same. Then there is no control at output side. This is very important. Based on this one only question is framed in GATE exam. Repeated question in GATE exams. That is, if the pi is the power factor angle, then for inductive loads, the output is controlled for pi to 180 degrees. For what range of firing angle output is controlled? If the question is asked, for what range of firing angle output is controlled pi to 180 degrees? For what range of firing angle output is not controlled, students? 0 to pi. For if the firing angle is 0 to pi, output is not controlled. If the firing angle is pi to 180, sir, how to calculate pi? Tan inverse XL by R. Okay, this is very important repeated model. For your exam also it is important. Then this is the question important that you have to come. For example, by giving this circuit, if they ask what is the uncontrolled range? Uncontrolled range is 0 to pi. Controlled range is pi to 180. Here the question is asking uncontrolled range. Na? Uncontrolled range, not controllable, means uncontrolled range, 0 to pi. What is pi? Tan inverse XL by R. What is XL here? This is XL. This is. Sometimes they don't give XL directly. They will give inductance. If inductance given, how to calculate XL? XL equal to 2 pi FL, students. Inductance is given, like this you calculate the XL. But here directly XL is given, no problem. Then tan inverse XL by R 50 by 50. Then tan inverse 145 degrees. That is 0 to 45 degrees output is not controlled. Then what range output is controlled? 45 to 180 degrees. This model is important. Next. From this also we can expect the questions. For RL load, these formulas also very important. What is the maximum value of average thyristor current? That is Vm by pi z. Maximum value of average thyristor current equal to Vm by pi z. Where z equal to square root R square plus XL square. What is the maximum value of RMS thyristor current? Vm by 2z. Very important formulas. Maximum value of RMS thyristor current equal to Vm by 2z for inductive loads. What is the maximum value of di by dt? Omega Vm by z. Omega Vm by z. But point to remember, students. In RL load case, if the firing angle is given less than 90 degrees, maximum voltage across the SCR depends on the firing angle. That you have to take Vm sin alpha. If alpha 30 degrees, Vm sin 30. If alpha equal 45 degrees, Vm sin 45. If the firing angle is greater than or equal to 90 degrees, what is the maximum voltage across the any SCR? It is asked Vm only. It is independent of firing angle. Greater than or equal 90 degrees, 135, 140, any firing angle it is given. You take directly peak, that is the maximum voltage across the SCR is Vm. But if the firing angle is less than 90 degrees, you have to take the maximum voltage across the SCR is Vm sin alpha. In phase control, for small firing angles, we know that in AC voltage controllers, there is a two control techniques are there. Phase control technique, another one is on-off control technique. In AC voltage controllers, this note point I am giving. AC voltage controllers. The voltage control techniques are voltage control techniques. What are the voltage control techniques? One is a phase control technique. What do you mean by phase control? By controlling firing angle, RMS output voltage is controlled. Then on-off control technique. Next we have to see that technique also. On-off control technique, it is also called integral cycle control technique or burst firing control. In phase control technique, output voltage is high, output waveform is less distorted for small firing angle. That is, in phase control techniques, if you use a small firing angle control, very low firing angles if you use, then output is not distorted more. It's nearly sinusoidal and output voltage is also high. If you use the large firing angles, if you increase the firing angle for very large value, if you operate for very large firing angles, I am getting the output like this, friends. This is the more distorted waveform. If it is a more distorted waveform, it introduces the more number of harmonics into the load. That is the problem. That is for large firing angles. If you use the large firing angles in a phase control technique, output is less, output is more distorted and introduces more number of harmonics into the load. That is the problem. That's the reason why hence phase control technique is more preferable for small firing angles or large firing angles. More preferable only for small firing angles. Don't use for large firing angles. Small firing angles means large output voltage or small output voltage. If firing angle is less, friends, if firing angle is less, the output voltage is more. Firing angle is less, then large output voltages are This is preferable. That point mainly you have to consider. And one more control technique is integral cycle control or on-off control, students. In integral cycle control or on-off control, by controlling the on number of cycles and off number of cycles, by controlling on number of cycles and off number of cycles, the output is controlled. That is nothing but integral cycle control. This is also called burst firing control. Integral cycle control is also called burst firing control, students. Then let assume that we are applying this integral cycle control for full wave AC voltage controllers. Full wave AC voltage controllers. Positive half cycle T1 is controlled, negative half cycle T2 is controlled. Again positive half cycle T1, negative half cycle T2. Like this. Some cycles we are controlling the output voltage. Some cycles. During some cycles completely off. This is on number of cycles. This is off number of cycles. Again on number of cycles, off number of cycles. That is the meaning. On, off. Some cycles we can control, some cycles completely off. Here T1 on, T2 on, T1 on, T2 on, T1 on, T2 on. But here T1 is off and T2 is also off. That is called on-off control. We don't trigger any thyristor during some cycles. During some cycles we trigger T1 and T2. Positive half cycle T1, negative half cycle T2. During some cycles we don't trigger any thyristor. This type of control is called on-off control. Let n is the on number of cycles, m is the off number of cycles, friends. Important formulas you can get here. N is the on number of cycles, m is the off number of cycles. Then you have to define total time period equal 2 pi into m plus n. What is n here? On number of cycles. What is m here? Off number of cycles. Then we can also define duty cycles, friends. Duty cycle equal to on time by total time period. That is on cycles by on number of cycles by on number of cycles plus off number of cycles. This is called duty cycle. Duty cycle is denoted by K here. Important formula. In on-off control of AC voltage controller, by giving on number of cycles and off number of cycles, if it is asked what the duty cycle, use this formula. In on-off control, what the RMS output voltage? Vs into root K, where K is the duty cycle. How to calculate duty cycle, you know. What the input power factor? Very important, friends. Input power factor equal to root K. Just by giving on number of cycles and off number of cycles. If they ask the what is the input power factor? First to calculate duty cycle, substitute here, we can get input power factor. Input power factor is root K. What is the output power, friends? Output power equal to K Vs square by R. That is V naught RMS square by R na. V naught RMS already you know. V naught RMS equal to, this is important formula. V naught RMS equal to Vs into square root n by m plus n. That is Vs into root K square. This is the output power expression. What the average value of each thyristor current? K Im by pi. Concentrate. Average value of each thyristor current equal to K Im by pi, where Im equal to Vm by R. This is the maximum current strength. What is the RMS value of each thyristor current? Im by 2 into root K. These formulas are important to solve any problem with respect to on-off control technique. Point to remember, friends, phase control is preferable for lighting control technique. For lighting control, phase control is more preferable. On-off control is more preferable for heating control. And one of the main applications of this AC voltage controllers is fan drives. AC voltage controllers more preferable for the fan drives. AC voltage controllers. Note. AC voltage controllers. AC voltage controllers more preferable for fan drives. Preferable for fan drive application. For fan control, these are more preferable. And this is the practice question with respect to on-off control. The given supply voltage, resistance they given, on number of cycles are 6, off number of cycles are 4. Calculate RMS output voltage, input power factor, average and RMS thyristor current. Then V naught RMS equal to Vs into root K na, RMS voltage. Duty cycle is N by M plus N, on cycles by off cycles plus on cycles. 0.6 I got. This is the RMS voltage, friends. How to calculate input power factor? Root K. This is the input power factor. How to calculate average thyristor current? Average thyristor current equal to KIM by pi, friends. KIM, how to calculate? Vm by R. Don't forget this one. Im equal to Vm by R. Vm is root 2 Vs. Root 2 Vs equal to Vm, friend. Then how to calculate RMS thyristor current? RMS thyristor current equal to Im by 2 into root K. Like this, we have to solve the problem based on-off control cycle or integral cycle control. With this, AC voltage controllers are completed. And one more topic with respect to module 5, I am giving the cyclo converters. What do you mean by cyclo converters? The static power electronic circuit which converts AC to AC, AC to AC with variable voltage and variable frequency. That in cycloconverter at output side voltage is variable, frequency is also variable. We can step up the frequency or step down the frequency. In cycloconverters, we can step up the frequency or step down the frequency. That is very important. Both step up and step down operation of is possible in the cycloconverters. And these points, the cycloconverter normally used to provide either variable frequency from a fixed, this is important. We can get the variable frequency from fixed input frequency or a fixed frequency from a variable input frequency. Not only step up the frequency and step down the frequency. We can get the variable frequency from fixed frequency or we may get the fixed frequency from the variable frequency. A cycloconverter can handle load of any power factor and allows power flow in both the direction. This is important. The quality of the output voltage wave and its harmonics distortion also impose the restriction on this frequency. This distortion is very low at low output frequency. This is important. Cycloconverters are more favorable for low frequency. The distortion is very low at low output frequency. For low output frequency, the distortion is very less. For example, in the option they given different frequencies. For which frequency it is more favorable, it is given like that. Then your answer is for low frequency, it is more favorable because distortion is less. Then what are the types of cycloconverters? Based on supply frequency, the cycloconverters are step down cycloconverter, step up cycloconverter. In based on supply frequency. In step down cycloconverter, output frequency less than the input frequency. In step up cycloconverter, output frequency greater than the input frequency. Based on configuration, midpoint type cycloconverter, bridge type cycloconverter. Based on output input number of phases, single phase to single phase. That is, we can control from single phase to single phase. Three phase to three phase is also exist. Three phase to single phase is also possible. But single phase to three phase is not exist. In cycloconverter, three phase to single phase is also possible. Then this is the application of cycloconverters important. Application of cycloconverters are important. Induction heating application, speed control of high power AC drives, static wear compensation important. For converting variable speed of alternator voltage to constant frequency output voltage for use of power supply. Aircraft and shipboards also we can use cycloconverter. Aircraft and shipboards, very important applications that you have to concentrate. Then single phase to single phase midpoint type cycloconverter. This single phase to single phase midpoint type cycloconverter, first you have to concentrate how many number of thyristors, number of SCR series. Single phase to single phase midpoint type cycloconverter, number of SCRs equal to 4. No need to concentrate on the operation. What is the single phase to single phase midpoint type cycloconverter peak inverse voltage? Peak inverse voltage is 2 Vm. That is, we can operate this cycloconverter, we can operate in both step up mode and step down mode. First here I am explaining step down mode. Step down mode means we are step down the frequency. Let us assume that f naught equal to fs by 3. What do you mean by f naught equal to fs by 3? For three cycles of input, we have to get one cycle of output. That is step down. Input is 3 cycles, 1, 2, 3. But output is how many cycles? Output is only one cycle we are getting, students. This is called f naught equal to fs by 3. Simply remember how to identify how many input cycles, how many output cycles, students. This denominator indicate the input cycles. Denominator indicate the input cycles. Numerator coefficient indicate the output cycles. Numerator coefficient indicate the output cycles. Here, what is the coefficient? 1? 1 output cycle. What is the denominator? Input cycle. Like that you have to identify. Always denominator gives the input cycle. Numerator coefficient indicate the output cycles. Denominator indicates the input cycles. That is, if denominator is odd number, if it is odd number, the sequence of conduction equal P1, P2, P1, P2, P1, P2, P1, N1, N2, N1. Like this, the devices will conduct. If it is odd number, the devices are conducting. P1 how many times it is conducted? 2 times. P2 only 1 time. N1 how many times it is conducted? 2 times. But N2 only 1 time. That is, in step down cycloconverter, before that this point you remember, in step down cycloconverter, what type of commutation we have to use? This is important. Natural commutation or line commutation. No need to use the forced commutation here. In step down cycloconverter, which commutation we have to use? Then the conduction angle of devices are not equal if it is an odd number. This statement I given. In step down cycloconverter, if F naught equal to A into Fs by N form, Fs is the supply frequency. A is the output number of cycles, N is the input number of cycles. If N is the even number, all the devices conducting with same angles, friends. If N is the odd number, devices are conducting with different angles. And one more point to remember, in step down operation, first positive, the group, all the group, positive group, next negative group, again positive group. Alternative like this you can, positive, totally first positive group, next negative group, again positive group, like this. But in the case of step up, alternative you can get positive, negative group. P means positive group, assume that. N is negative group. That means in step down operation, first all the group of devices, one group of devices will conduct, next another group of devices will conduct. That is the meaning. And if it is an odd number, the conduction angles are different. If it is an even number, all the devices conducting with the same angle. Then you have to see the step up operation. F naught equal to Fs. Here denominator is 1. Always denominator is input cycle I told. This coefficient is the output cycles. Like, simply you can remember like this. That is how many input cycles? 1 input cycle. How many output cycles? 2 output cycles. Then we have to make the devices like this. Then what is the sequence of conduction? P1, N2, P2, N1. That is in step-up cycloconverter, which commutation we can use, friends? Forced commutation we can use. That is in step-up operation, what the conduction sequence you see? First positive group, next negative, positive, negative. Alternatively it is conducting. But in this case, totally one group, next another group. But here alternatively the devices are conducting in the case of step-up operation. How to identify output cycles and input cycles, that I told already. Like this you have to identify. Then this is a single phase to single phase bridge type cycloconverter. How many number of SCRs? 8 SCRs. This peak inverse voltage is Vm. In midpoint type cycloconverter, at a time how many devices are conducting? Only one device is conducting. But the waveform is same here. At a time 2 devices are conducting here. At a time 2 devices. First all the positive group, all the negative group. If it is an odd number, device conduction angles are different. If it is even number, device conduction angles are same. Whatever midpoint type, here also same points, but only difference is in midpoint type peak inverse voltage is 2 Vm, but in bridge type cycloconverter peak inverse voltage is Vm. But here at a time 2 devices are conducting, but in midpoint type cycloconverter at a time 1 device is conducting. It is a step down operation. In step down operation, which commutation we can use? Natural commutation or line commutation. In step up operation, which commutation we can use? Forced commutation we can use. In step-up cycloconverter, alternatively, positive group, negative group, positive group, negative group. Like that devices will conduct. Easy to remember, student. Sequence also they will ask. Like this you remember only. Next. All these are the single phase to single phase cycloconverter, students. In single phase to single phase cycloconverter, if they ask what is the RMS output voltage, still now not asked in any competitive exam, but you can expect. This is similar to full wave AC voltage controller formula. Vm by root 2 pi into pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by 2. What is the input power factor? These formulas are applicable only for single phase to single phase, friends. What is the average output voltage? 0. Next. Some points mainly you have to concentrate with respect to 3-phase cycloconverter. 3-phase cycloconverters are very important for competitive exam point of view. In a 3-phase 3-pulse cycloconverter, how many number of SCRs are required? 18 SCRs are required. In 3-phase to 3-pulse cycloconverter, 18 thyristors are required. In 3-phase 6-pulse cycloconverter, how many SCRs are required? 36 SCRs are required. In 3-phase 6-pulse cycloconverter, how many number of SCRs are required? 36 SCRs are required. And one more point you have to remember, if number of pulses are increases, harmonics will reduce. 3-phase 3-pulse 18 SCRs. 3-phase 6-pulse cycloconverter 36 SCR. That is, in any cycloconverter, if number of pulses are increases, harmonics will reduce. To increase the number of pulses, the number of SCRs we have to increase. That means if the number of SCRs are increases, harmonics will reduce. Then average output voltage of 6 pulse, not average, RMS output. Output voltage here, output means RMS output. Average value always 0. RMS output voltage of 6 pulse cycloconverter is 2 times of RMS output voltage of 3 pulse cycloconverter. Then power output of 6 pulse cycloconverter is 4 times of as compared to 3 pulse cycloconverter. Voltage is 2 times, but power is 4 times as compared to 3 pulse cycloconverter. Next, I told already in cycloconverter there is a three phase to single phase conversion is also exist now. To get the three phase to single phase, then how we can control the firing angles? We are converting three phase to single phase now. To get the single phase output in cycloconverters, to get the positive off cycle, the firing angle is controlled as 90 degrees to 0 degrees and 0 to 90 degrees. Then only we can get positive output. Very important observation. This is for to convert three phase to single phase. Single phase to single phase, any firing angle you maintain, no problem. Three phase to three phase, you control the firing angle or not control the firing angle, no problem. But if you want to convert three phase to single phase, we must to control the firing angle. Otherwise, it is not possible. But how we can control the firing angle? To get the positive off cycle output 90 to 0, 0 to 90. To get the negative off cycle output 90 to 180, 180 to 90, firing angle is controlled. In three phase to three phase and single phase to single phase cyclone converter, the firing angle is maintained either constant or variable, no problem. But in three phase to single phase, firing angle must be variable, friends. Firing angle must be variable. Next. This is very important. Even gate point of view also, from this formula we can expect the question. In three phase cycloconverter, what is the RMS value of fundamental output voltage? Gamma into V phase into M by pi into sin of pi by M. This is three phase cycloconverter formula. For three pulse, this is the formula for three pulse. We have to use V phase value. This we have to use the V phase. For three pulse, you use the V phase value. Where M is the number of pulses. Where gamma is the reduction factor, voltage reduction factor. If voltage reduction factor is not given, you take 1 students. If voltage reduction factor is not given, you take 1. Same formula we can also apply for 6 pulse cycloconverter, but instead of phase value, here you take the line value. See the difference. Both are same formulas, but only difference is for 3 pulse cycloconverter, you have to use the phase value. For 6 pulse cycloconverter, replace V phase by VL. Where gamma is the voltage reduction factor. If the voltage reduction factor is not given, you take the gamma equal to 1 students. In load commutated cycloconverter, load must be consist of battery, then only load commutation is possible. How many switches? This is one question. How many switches are required to construct 3 phase to 3 phase cyclo? 3 phase to 3 phase cycloconverter, 18 thyristors are required. To get minimum harmonic distortion in the output, 3 phase to 3 phase cycloconverter, number of SCRs. Minimum harmonics means more number of SCRs, that is 18, maximum is 36 SCRs are required. In 3 phase to 3 phase cycloconverter, supply is 400 volts 50 Hz. For 3 pulse, calculate the fundamental output. For 6 pulse, calculate the fundamental RMS output. For 3 pulse, we have to use the phase value. In 3 phase, whatever the voltage given, that is the line value. But you have to substitute phase value, 400 by root 3. 6 pulse directly substitute the line value. Line value is how much? 400. That you have to consider. This model of question you have to practice, friends. These two models important for your exam point of view also. Even though syllabus is not given, you please go through the minimum points. That is very important. And this problem you try to homework for practice. Try to practice this problem. And this problem also you try to practice. Single phase bridge type cycloconverter. All the formulas that I given students, please go through this formula. Friends, with this, with respect to module 5, the AC voltage controllers and cycloconverters concept is completed. This about the session. Thank you. With the total module 5, all the power electronic quick revision is completed. With this, power electronics, all the concepts are completed. Module 1, I discussed power semiconductor devices. Module 2, I discussed rectifiers. Module 3, choppers, that is DC to DC converters I given. Module 4 that I given inverters, friends. Inverters that I given. Module 5 AC voltage controllers and cycloconverters also completed. That is the important observations from power electronics according to your gate syllabus all are completed. That is about the quick revision of the power electronics subject. Thank you very much and wish you all the best for your exam. Thank you.